Last of all, we need to solve for equilibrium in this model and remove any nominal variables so that all we have left are real variables, including inflation. So let's start with the government. The government has no expenses, and that means that its revenue, which is the amount that it raises by increasing the money supply, plus the amount that it gets from taxing people, has to equal 0. And of course, we can easily rearrange this to show that this pins down the tax rate. If we assume that the government has no expenses and has a balanced budget, that implies that in equilibrium, we're going to have that the lump sum tax equals this. Notice that means that if the money supply is increasing, then the lump sum tax is actually a negative number. In other words, what the government is doing is raising seigniorage and distributing it to the population. Next, let's look at the agent's budget constraint. This is the agent's budget constraint, and since we have this result for what t is in equilibrium, we can write that in here. These two minus signs will cancel, and these two price levels will cancel. And of course, that means that we can remove these common terms from both sides. Next, there is zero net supply. Since households are identical, that means that B has to equal 0 at all dates. And so in equilibrium, that disappears. Of course, the agents have locally non-satiated preferences, so we have to change this to an equal sign. Next, we can divide both sides by the price level. And so this just becomes the real wage, and this is real profits. Now you may recall we have an expression for real profits, so let's bring that down. Real profits were defined this way, and so this is going to be the real profits from all the firms. So we will have to replace this with this, and then just integrate over all the firms. We can replace profits here with this expression. And notice that W over P is just little w, the real wage. We can write this in the following way by separating the two parts of the integral. And notice that since this is a common wage for everyone, setting the condition that demand for labor has to equal supply is just NT. And of course, these two terms cancel, and we're left with this. Now, recalling that this is the demand function for each individual intermediate, we can insert that expression into this equation, and we can simplify, because all we need to do is add 1 to this power. Furthermore, we can take this outside the integral, because it does not depend on j. Last step, recall that we have an expression for the aggregate price index, which is this, which you may recall from earlier. We can take this and insert this expression into this equation. Now, before doing that, notice that P here doesn't depend on J, so we can just pull it out, making sure to apply the appropriate power. And now, if we replace this here, you can see that this is going to simplify. We multiply these exponents and they equal 1. And then this is just equal to this. They equal 1. And we're left with the condition that C has to equal Y. To do that, consider the following. Here is our expression for the demand for an individual intermediate. And notice that we can rewrite that in terms of A and N, because that's the production function. Now, since this is true for all J, it's got to be true if we integrate over J. Notice that this doesn't depend on J, so it can come out. And notice that this is total labor demand, which has to equal total labor supply. And notice that this can come out as well, because it doesn't depend on J. Finally, define the following. We call it V of P, and we're going to define it as this thing. So it's going to be a summary statistic for the distribution of prices. Therefore, we can write the following. We have that moving this to the other side, output equals this. We can just replace this expression with VP, divide both sides by VP, and we get the output equals this. So it equals total production, total labor, and this term, which summarizes the distortions that arise from having all these different prices for what's essentially the same good, or different versions of it that are imperfect substitutes. And this is important because we'll see that this variable is going to follow a simple difference equation, and so once again we're going to end up preserving the recursive structure of this whole model without having to worry about tracking the entire price distribution. We now have 14 variables and 14 equations that characterize their equilibrium behavior. That said, there's still some tasks we have to complete before we wrap this up. In particular, we would like to remove any nominal variables that remain in the system. And by that, I mean the price level and the distribution of prices. So, for example, let's consider one of our conditions, the Euler equation. This is the Euler equation for the household, and you will see that it has the price level in there. However, what we're going to do is the following. Define pi sub t to equal the ratio of the price level today to the price level yesterday minus 1. In other words, this is a measure of inflation. It's pretty straightforward to see that we can replace this with simply 1 plus pi t plus 1. So now we've gone and put the Euler equation for the household in real terms. Next, we'll have the money demand function. Now, the money demand function is almost there. We just need to define small mt to equal real money balances. And this one can be very easily rewritten, noticing that this is just mt to the minus 1. Alternatively, cross-multiplying everything, we could have just m sub t equals that. We switch these two. Multiply by theta, and we're done with money demand. Next, let's get rid of heterogeneity in the price level. You know that this is the link between the aggregate price level and the prices of individual intermediates. Notice that a fraction 1 minus phi of these firms update their prices to p sub t star, and the rest, which of course is a measure phi, keep the same prices as before. How is that going to tell us that prices evolve? First of all, let's raise both sides to the power of 1 minus epsilon. So we have this relationship. This is going to equal the following. Let's arrange the firms so that the firms with names from 0 up to 1 minus phi are the ones who update their prices. So they will adopt pi star. This will be to the 1 minus epsilon. And let's say it's the ones with names 1 minus phi to 1 who do not change their prices. And since who gets to change their price is random, that means that the distribution of prices over these guys is going to be the same as it was yesterday. Don't forget to put the time index in there. Now this we can continue to simplify because notice the following. This doesn't depend on j, so it can just come out. And this, of course, is simply nothing more than 1 minus phi. What about this? Well, notice that this is just essentially a scaled down version of yesterday's distribution of prices, one with mass phi. So this is simply equal to the same thing, and this is just phi times the distribution from 0 to 1. What is this? Well, notice from this expression that this is nothing more than simply pt minus 1 to the power of 1 minus epsilon. So, to cut a long story short, we have shown that the aggregate price distribution actually follows this very simple law of motion. Last but not least, p is a nominal variable, so we want to get rid of it and write it in some way that connects it to inflation. And the natural thing to do here is to divide both sides of this equation by pt minus 1 to the 1 minus epsilon. So we'll divide that there, and there, and there. Define pi star to be inflation as before, except that it's only reflecting inflation for the firms that actually get to update their prices. And now we can simplify this as follows. This cancels. And notice this is simply 1 plus inflation to the 1 minus epsilon. And this is also 1 plus pi but only for the updating firms, again to the power of 1 minus epsilon. We can use the same trick to simplify VP. Remember, this is an auxiliary variable that helps us track the price distribution, or rather inefficiency due to price dispersion. Here's the expression that defines it. And just as before, if we order people's names based on whether or not they're updating, you're going to have two parts. One is going to be the folks from 0 to 1 minus phi. And these are the folks who actually got to update their prices. So their price today is P star. And then you have the folks from 1 minus phi to 1. And their price is the same as it was yesterday. There. Next, notice that this does not depend on j, so we can pull it out. And this integral simplifies to simply 1 minus phi. What about here? Remember, this is just a compressed version of the entire price distribution yesterday because people are selected randomly. So this is just phi times the full value of this integrand. Let's multiply and divide this by p sub t minus 1 all to the minus epsilon. And why are we doing that? We're doing it because this is going to simplify a lot. Notice we can do this and this. And now you see where this is going. What's this expression? This is 1 plus pi star. What's this expression? It's 1 over 1 plus pi. And what's this? Well, we're almost there. Let's do the same thing. Let's multiply and divide this by pt minus 1. Again, we can switch these terms. And what do we see? Well, first of all, this can come out because it doesn't depend on j. And what is this? It's simply 1 over 1 plus inflation. So this becomes 1 plus pi sub t, and this becomes epsilon instead of minus epsilon. And what do we have in here? Well, this is exactly this expression here, except that it's at date t minus 1. So that is v of p dated t minus 1. So now, again, we've eliminated prices and indeed the entire price distribution from the system. That's the wonderful convenience of Calvo pricing. Now, finally, you remember also that we have these auxiliary variables, where this actually should be P star. It's the optimal price that a firm would choose if they're allowed to select their prices freely. Now we're going to want to make all of this in real terms. And so to start, let's define the following two variables. Let little x 1 of t be defined as big X1 divided by the price level to the power of epsilon. And let's define X2 as big X2 divided by the price level to the epsilon minus 1. You can see that the price level appears that way in each of these expressions. So, starting with this one, let's see what we get. We take this and write it here instead. And we can split this into two parts. This one and this one. Now notice that this cancels. And what about this one? Well, let's multiply and divide this by p t plus 1 to the epsilon. And why would we want to do this? Well, observe that I can switch these terms. And now you can see that this is simply 1 plus pi t plus 1 to the epsilon. And this divided by this, well, what is it? It's just little x. So now we found an expression for how x1 evolves over time without any nominal variables being in there. Similarly, we can do the same for x2. So let's replace this expression in here. Once again, we'll have two terms. So let's have the first one here and the second one here. Very clearly, we're going to have something very similar happening. P to the epsilon minus 1 is going to cancel out of here. And what do we do over here? Again, let's multiply by this, except that now, instead of the power of epsilon, we need the power of epsilon minus 1 if it's going to give us anything useful. We can switch these two again. And once more, what's this? This is simply 1 plus pi tomorrow. Don't forget the power. And what's this? Big X2 over P to the epsilon minus 1. Well, that is just little x2. So once again, we found a recursive formulation for our auxiliary variables that does not involve any nominal variables. Finally, take this expression for how the optimal price varies over time. Why don't we multiply top and bottom by pt to the epsilon minus 1. And what's going to happen now? Well, notice I can rewrite this as follows. And that means that I can just pull this out in front, because the inverse of the inverse is itself. I'm going to move this over here. I'm going to move this over here. What are we going to get? Well, x1 divided by pt to the epsilon is just little x1. And x2 divided by pt to the epsilon minus 1 is just little x2. Finally, let's divide both sides of this by pt minus 1. And what are we going to get? Well, this is simply 1 plus pi star, and this is simply 1 plus pi. So now our auxiliary variables, instead of telling us how the price level evolves, are telling us about how inflation evolves. We're almost there. So now, remember that the law of motion for money was defined in nominal terms. So let's define delta log of real balances, and we're going to define it as the log of real balances today minus the log of real balances yesterday. And since little m of t, real balances, equals big M divided by the price level, this is going to be the same thing as the log of big MT minus log of big MT minus 1 minus the log of prices plus the log of prices the previous period. And of course that's just equal to delta log of big MT, as defined earlier, minus the log of 1 plus pi t. Now before we had that delta log mt follows a particular law of motion, and it was 1 minus rho sub m 1 minus rho sub m times some pi times rho sub m times delta log m t minus 1 plus an error term. So now we want to rewrite this. We want to rewrite it in terms of delta of small m. So we can take this equation, which we know reduces to this, and replace it with the following. Now we still have delta log of mt minus 1 floating around here. How do we get rid of that? Well, using this equation, we know that delta log of big MT is delta log of small mt plus the log of 1 plus inflation. So let's just use that. So we're going to get rho m times this, except that it's at t minus 1, plus this, except that that's also at t minus 1. So distributing rho across these two terms, we end up with this, which again is only in terms of real variables and inflation. Now, very often you won't actually see this equation. Instead, because the inflation rates typically used in these models are small, and because macroeconomists like to take log linear approximations of things, as you probably know, the log of 1 plus something small is approximately equal to something small. So very often this is written simply as follows. There, excellent. So to sum up, we are done. We have 14 variables, I should say 14 real variables, and those are consumption, the interest rate, labor, the real wage, the marginal cost, productivity, output, our variable that captures price dispersion, inflation on average, inflation among those who get to optimize their prices, our auxiliary variables x1 and x2, real money balances, delta log of small mt, and that should yield 14 variables. And to solve them, we have 14 difference equations. The Euler equation for the household. Then we're going to have the labor decision for the household. Then we're going to have the household money balances decision. Then we're going to have the definition of the marginal cost, which is this. Then we're going to have the equilibrium condition, which is that C is Y. That's because we don't have investment here. We're going to have the relationship between output and our variable VP, which tracks the impact of price dispersion. We're going to have the law of motion for VP, which is this. There. We're going to have two equations for inflation. One is this one, and the other is this one, which relates to our auxiliary variables. We will, of course, need the equations for how these auxiliary variables change over time. And finally, we will have the laws of motion for our variables. This is one law of motion. We'll also need the definition of delta log m, which you'll recall is simply log m minus log m t minus 1. And finally, the last equation is the law of motion for productivity, which is simply log a equals rho a of log a t minus 1 plus a disturbance. And that's it. What's the point of these 14 equations? These 14 equations are something you could easily type into Dynare to simulate this model, given some parameters that you made up. And so in the description, I'm going to post a Dynare program that you could use to simulate the model that we discussed. So today we focused on Calvo pricing without investment, without any other frictions or features that you typically find in New Keynesian models or DSGE models. The point was just to make sure that you have some initial exposure to how Calvo pricing works. In reality, this is just one of the many features that a typical DSGE model may have. And so now you're equipped to go and add new complications. I hope you found this useful. Keep calm and carry on studying macroeconomics.